So, I just wish to inform you that yesterday's lecture had been uploaded in the stream videos channel, and you can go back and visit that if you have missed some part or the whole of the lecture. So, you can go back and you can view that video and like to your own satisfaction. So, let me start with the course. So, yesterday what we had done, we had given a brief introduction and discussed some mathematical fundamentals, some math fundamentals which are very useful to go ahead in this course, and we will see that the ideas which we had discussed, the ideas of slope will come forward when we are working with the electronic circuits. I also told you that some idea of physics will also come into play, because we will understand how the behavior of the particular material that we will be dealing with, how the material is behaving from the physics point of view, and then that behavior will come in form of some mathematical equation, some plot of VI graph, and then when we have a plot, then we can do all sorts of mathematical operations with that plot, and with the help of those we will actually get the formulas that we will use to solve our circuits. So, let us start with this course now. So, I will actually go through the textbook of Malvino, and I have a PDF which I will share. I will not go verbatim, but I will just point out a few parts of the book which are the main parts, but I suggest that you go through the entire chapter from first to last, which will have more clear idea of the entire thing. So, is this visible, this semiconductors written here? The screen share is visible
Yes.
to all of you?
Yes,
Sir.
Yeah.
yes, sir.
Okay, okay. So, the main difference between the other courses that you are going to study and this particular course is that the element through which we will pass the current, or so as to say that the element across which we will apply a voltage will not be a metallic element, or you have studied about metals, you know that they have some conductivity, they are highly conductive, so current passes through them easily, the resistance is very low. Also, you have studied about materials which pose a very high resistance to the flow of current, and we use those sort of materials as resistors. So, the material that is mostly used as resistors to build resistors is carbon, and we have carbon resistors, and other resistors are also there. So, what we are going to study in this particular course is the behavior of the behavior to pass current through semiconductor materials. So, you have studied semiconductors probably in your 11-12 physics course, a bit about semiconductors. We will go a bit more into the behavior of the semiconductors in this course during the start of this course, to understand what exactly happens when we have a semiconductor, when we have a voltage applied across the semiconductor, and what we can do, what special thing we can do with the semiconductors, which actually makes this whole domain of electronics different from normal or usual electrical circuit analysis. The usual electrical circuit analysis involves the electrical elements such as resistance, inductance and capacitance. All those are linear elements. However, the semiconductors give us flexibility to work with these elements to make them nonlinear in nature. And when we can get this nonlinearity, this nonlinear behavior in the circuit, it gives a lot of different application oriented use for those circuits. So we will see those applications also, but first we need to understand how the semiconductors actually behave and how we are able to extract these nonlinear property from the semiconductors. So let us go ahead. So what are semiconductors? We all know that they are those class of materials which lie, whose conductivity lie between conductors and insulators. And what are conductors? Conductors are mostly metals. So they are normally having a single electron in the outer orbit. So like metals like copper atom and all, you see the copper atom here. So there are stable shells, stable orbits of electrons. However, the outer orbit is having only one electron, and this electron is so far away from the core that it experiences very little attraction to the core. So it is almost free, and a very small external force can dislodge this this electron from the atom. However, when this electron is dislodged, it does not leave the copper, the entire copper lattice. It does not leave it. It stays within that lattice, but not attached to a particular atom. So what happens? There is a cloud of electrons inside the copper wire or copper block, whatever, inside that copper thing, there is a cloud of electrons. And now if you apply a force from outside, an electrostatic force from outside, by applying a potential difference across this copper, then what will happen? That these electrons will get attracted towards the positive side of the potential difference. Suppose we have created the potential difference using a battery, so the electrons will start getting attracted towards the positive polarity of the battery, and this will result a current through this copper block. Suppose there is a copper block, it will result in a current through this copper block. What would happen to semiconductors? What are semiconductors? Semiconductors are like this. You see, the base conductors will have one valence electron, whereas the base insulators will have 8 valence electrons. Based insulators will have 8 valence electrons, and you know that when the outermost shell will have 8 electrons, it becomes a very stable configuration, and the electrons will not leave that orbit. Like it takes a very high amount of energy to make a electron leave that stable orbit. And a semiconductor, what is a semiconductor? This is an element where the electrical properties are between the conductor and an insulator, and as you might expect, the best semiconductors will have 4 valence electrons. It will have 4 valence electrons. So some materials, germanium and silicon, previously when this work with semiconductors started, then germanium was very much used because that time the silicon devices were not coming up because of some issue in extracting silicon in pure form. However, germanium had a very fatal flaw, You see it is mentioned here, is having a very fatal flaw. What is that fatal flaw? We will learn about this later. They have very excessive reverse current. We don't know right now what is reverse current, but we will learn about this later on. So they had a very excessive reverse current, and that is a very fatal flaw for germanium devices. So when the issues regarding refining problems of silicons were solved, then silicon became the material of choice for making the semiconductor devices. Okay. Now let us look into the atomic structure of a silicon atom. So unless it is mentioned otherwise, for all the devices that we will learn in this course, we will assume that we are talking about silicon devices. Please mark this and remember this, that unless it is mentioned otherwise, all the devices that we will be talking about in this course will be silicon devices. Okay. If we are talking about germanium devices, we will mention it that it is a germanium device. Unless there is nothing mentioned, we should assume automatically that we are talking about silicon device. So please make sure of this. So what we are studying here, we are looking at a silicon atom, and the silicon atom has atomic number of 14. That means there is 14 protons in the nucleus and 14 electrons in the orbit. So if there are 14 electrons in the orbit, 2 in the innermost shell, 8 in the next shell, so 10 is gone here, so 4 remains at the outside shell. So 4 in the outside shell. So it is like this. Okay. So what is the net charge here in the silicon atom? The net charge is 0 because there are equal number of protons and electrons. Okay. Now you see there is a small question asked here. What is the net charge of the silicon atom if it loses one of its valence electron? By what means it loses the electron, that is not told here, but suppose it loses one valence electron, then what would be its charge? Then obviously it becomes a positive ion, we all know about this. And if it gains an extra electron in the valence orbit, look, the valence orbit can hold up to 8 electrons. So there is a possibility of gaining an electron from outside also. So if it gains an electron, then it becomes a negative ion of charge -1. Now this is a single atom, single silicon atom, but whenever we face a silicon device, we are actually looking at a silicon crystal as a whole bunch of atoms together and in the form of a crystal. So what is the configuration there within the crystal? That is of importance to us. We must understand the crystal behavior, not a single atom behavior, but the behavior of the silicon crystal, because whenever we are going to handle a device, we are going to handle it in the crystal form. So you see here, this is the diagram of a silicon crystal, like a few of the atoms, and this happens all through the crystal actually. So what happens here, we must note this, that any atom, this is the atom, this is the nucleus, suppose the core, and this is the core is the proton and the innermost shells, and the outermost shell is only drawn here in the larger circle, and the inner circle is the proton plus the innermost shells. So we are concerned with the outermost shell only. So the outermost shell is here for this particular atom. Now what happens, there are neighborhood atoms, neighborhood silicon atoms to this particular atom. Now each of these neighborhood silicon atoms will donate one of its electron, to this central atom, so that the central atom will now have 8 valence electrons in its outermost shell. So once it has 8 valence electrons in its outermost shell, what will happen? This particular silicon atom will become a stable, will have a stable chemical configuration. So it will have, its outermost shell will have 8 valence electrons, and it will become a stable orbit, and the atom will also become a stable atom. So it will not try to accept any further electrons, nor it will try to give out any electrons. And in this way, this central atom is getting bonded with the neighborhood atoms, and we know what this bond is. We have learnt in chemistry that this bond is a covalent double bond, a covalent bond, and it is a double bond. So so this is a covalent bond. I think this is a single bond, sorry, these two electrons coming together to form one covalent bond.
Yes, sir.
Yeah. So here it is like two lines given, so suddenly it came to my mind double bond, but it is not double bond, it is a single one. So this is a thing. So I hope you understand this. And what happens, this particular neighborhood atom structure is repeating all through the crystal. So all the atoms are having 4 neighborhood atoms, and in this way all the atoms in the crystal are having their valence shell, outermost shell, filled up with 8 electrons and making covalent bonds with the neighborhood atoms. So this crystal is very stable crystal, chemically very stable crystal, the silicon crystal. Okay. So this phenomenon is called valence saturation, when the valence shell is having 8 number of electrons. This phenomenon is called valence saturation. So all the silicon atoms will experience this saturation and become stable. So when this is the case, that means the crystal, none of the atoms in the crystal will give out any electron, right? Because all the electrons are utilized to form valence, to give the valence saturation to all the atoms. So none of the electrons are going to come out of the atom. So because of this, a silicon crystal is almost a perfect insulator at room temperature. You see, this line is mentioned here. Okay, is almost a perfect insulator at room temperature. However, it can happen so that some electrons will be there outside the atoms. So what happens, you see, there is a phenomenon which happens, and there is a new concept which is not encountered with conductors as well as insulators. This concept of the hole is encountered in the semiconductor only. What happens? What happens is this, that the atmospheric air is having some temperature. Because of this, the heat energy in the air causes the silicon crystal to vibrate. So because of this temperature, because of the ambient temperature, all these atoms are not stationary, they are vibrating always. Always at any temperature, actually, if it is not absolute zero, any material will have their atoms in a vibrating state. They will have some sort of kinetic energy in them. So what is happening, because of these vibrations, notice this paragraph, because of these vibrations, occasionally some electron can be dislodged from the valence orbit. This is purely a mechanical phenomenon. The vibration is happening because of the ambient temperature, so there is some heat which is coming inside, which is causing the silicon crystal to get some heat, and this heat is causing a kinetic kinetic motion in the atoms. So there is a mechanical vibration, and this vibration sometimes causes a electron to be dislodged from the valence orbit. So when this happens, then what happens, this electron, when it is dislodged, that means it has gained some energy and it goes to a higher orbit. It goes to a higher orbit and it is a single electron in that higher orbit. In that larger orbit, it is a single electron. So it is a free electron, almost like the conductor. The conductors are also having a single electron in the outermost orbit. Here also the same thing happens. This electron getting dislodged from the valence orbit goes to a higher orbit and it becomes a free electron, a single electron in the outermost orbit, same as the conductor. But what is the difference? The difference is that in the conductor, the innermost shell is complete, all the innermost shells are complete. However, in this semiconductor, the electron that is dislodged makes the innermost shell, which was saturated, incomplete now. Do you understand? Do you get this point? Previously it was complete.
Yes, sir.
There was 8 electrons. Now from those 8 electrons, 1 electron has escaped and gone to a larger orbit. So this electron becomes a free electron. However, the orbit inside that, the secondmost outer orbit, does not have 8 electrons. It is not a complete orbit. So there is a hole there. So this is the concept of a hole. So this is this vacancy that has been created. You see, you read this paragraph, it is mentioned here. This vacancy that is created in the valence orbit is called a hole, and this hole behaves like a positive charge because the loss of the electron produces a positive ion. Now you can visualize the atom in this way. The electron has been dislodged from the valence shell, so the atom now becomes a completely positive ion and the electron becomes free. Okay, so there is a positive ion and an electron. In the conductor case, there is no positive ion. The free electron is from the very beginning of the metal. It is there always as a free electron. There is no creation of a positive ion. But in this case, the creation of a free electron makes the atom a positive ion, and this phenomenon of creating a vacancy in the valence shell is called a hole. The vacancy is called a hole, and this acts as a positive charge. Why? We know that the charges are those things like they can flow, right? The electron can flow. If there is a positive charge, if we are calling this a positive charge, it must have a capacity to flow through the crystal. But what we right now said, that it is a hole created within an atom, and the atom is fixed at a particular position. What happens is that the hole will attract and capture any electron from the immediate vicinity. This hole that is there in a particular atom will attract and capture an electron from the immediate vicinity. So what happens? An electron from the adjacent atom can come and fill up this hole. But when it happens like this, then the adjacent atom creates a hole there, because the electron that is coming from the adjacent atom to fill up the hole, that electron is coming from the valence shell of the adjacent atom. So the hole gets created in the adjacent atom. This is almost like that the hole is moving. Although the electron is getting dislodged from the adjacent atom and filling up the hole, but overall the phenomenon is like that the hole that has been created in the first atom is moving to the next atom, and in this way the hole can also move. So the hole will can also have a motion. So it is called a positive charge. Because of that, it behaves like a positive charge. You see here in this picture, so this sometimes due to this vibration and all, this electron can escape from the valence shell. So this electron is not associated with any atom right now. So this electron is a free electron, and this here a hole is created, and this hole can attract one electron from the adjacent atom, some of the adjacent. Suppose this electron is getting attracted, so this goes here, and the hole is moving from this position to this position. This is happening. So whatever we have discussed, and also there is another thing, that in the pure crystal, what happens, due to the ambient heat energy, there are some free electrons and holes getting created. Keep this in mind, that the number of free electrons will be equal to the number of holes, because the holes are only created when a electron escapes from the valence shell and becomes free. So the number of free electrons and the number of holes are same. I hope you get this. The number of free electrons and number of holes in a pure silicon crystal will be same. Now the free electrons can move randomly through the crystal. They are moving randomly through the crystal, and occasionally a free electron will approach a hole, feel its attraction and fall into it. So here a recombination can also happen. So there are, suppose there are 100 free electrons and 100 holes, but during the movement of the free electrons across the crystal, suppose 10 number of free electrons recombine with 10 holes. So now there are 90 free electrons and 90 holes remaining. So at any instant of time, what happens? Look at this main idea. This is why this book is so useful. I think that at the end of the chapter they also mention the main ideas from the chapter. So all this discussion, everything, you must remember these 3 points. At any instant in the pure silicon crystal, at any point of time, 3 phenomena are happening. Some free electrons and holes are being created by the ambient energy, thermal energy. Some free electrons and holes are recombining, and some free electrons and holes are existing. There is some already had been created. So they are existing, they are not recombining, they are not being created, they have already been created and they are existing there. Okay, so please keep this in mind. Sure. So if I ask you that at this particular room temperature, what is the number of free electrons and holes in a silicon crystal, there is no one answer, because at every instant of time some new free electrons and holes are getting created, some are getting recombined. So we don't exactly know how many number of free electrons and holes are there. However, there can be some approximate numbers given, like for in an example like this it has been asked, you see example 2.3, if a pure silicon crystal has 1 million free holes inside it, how many free electrons inside it, how many holes does it have? We have already learned that free electrons, number of free electrons and number of holes are same, because only due to the electron getting freed up, the hole is getting created. So the number of free electrons equal to number of holes. What happens to the number of free electrons and holes if the ambient temperature increases? So this is a conceptual question. Obviously you will understand, since the ambient temperature increases, more number of free electrons and holes will occur in the crystal, because more number of electrons will get freed from the valence shell. Someone was trying to ask some question.
Yes, sir.
Yeah.
Sir, if the thermal energy is the reason for the creation of hole, then there will be some energy when they recombine, release.
When they recombine, there will be some energy released also. Yes.
Okay, sir.
It will be released also. However, we are not very much concerned about the exchange of energy right now. Okay. How much temperature increase, decrease, then these are also questions that one can ask, but we are not bothered with those questions. But surely what you have said is correct. So when I am discussing like this, showing a page and discussing through it, I am unable to see if there are hands raised up. So whenever I give a pause or something, if you have a question, please raise your voice and ask it, because I am unable to see whether there is a hand raised up. Okay. So this is what is happening in a pure silicon crystal. Well, let us again wind our minds around the concept that we have learnt right now. So what we are doing, we are looking at semiconductors in this course. We are by default looking at silicon crystals, and in the silicon crystal, in a silicon atom, there are 4 outside electrons. However, when they form a crystal, then they bond with neighboring silicon atoms and saturate their valence shell. But this situation is not permanent in nature due to thermal energy coming from outside. Some electrons from the valence shell can get dislodged, so it forms free electrons, and one free electron gives rise to a hole in the valence shell. And at any instant of time within the pure silicon crystal, there would be some number of free electrons and holes existing, some number of free electrons and holes getting created, and some number of free electrons and holes getting recombined with each other. So this is about the pure silicon crystal, and that is called intrinsic semiconductor. Intrinsic semiconductor is a pure semiconductor. So a silicon crystal is an intrinsic semiconductor if every atom in the crystal is a silicon atom. There is no impurity in this semiconductor. It is totally a silicon crystal. No other atoms than silicon is there. So at the room temperature, how it will behave? There are certainly some number of free electrons and holes. However, this number is not very large. In a conductor, the number of free electrons are multiple fold times than the number of free electrons and holes in a semiconductor. That's what gives it the conductivity, right? So the semiconductor at room temperature, a pure semiconductor at room temperature, behaves almost like an insulator. If you give a potential difference across it, obviously the electrons and holes will try to flow. Holes are not flowing, the electrons are flowing, getting recombined with holes. It seems that the holes are also moving. So the electrons will move towards the positive charge, holes will move towards the negative charge. gives rise to a current, no doubt. However, this current is very small in nature, so it is almost behaving like a insulator. So you see the flow of free electrons and flow of holes are discussed here. So whenever you have charged metallic plates across a silicon crystal, then the free electron will be repelled by the negatively charged plate and will be attracted by the positively charged plate. So this free electron can move from one large orbit to the next and until it reaches the positive plate. So you remember that the free electron is not in the valence shell but in a shell in an orbit higher than that, and that's the reason why it is free, because it experiences almost negligible attraction to the core. So when there is a potential difference applied across this crystal, the free electron will move from the negative potential to the positive potential. How the flow of holes happen? So you notice this is the diagram. This free electron is here, it is flowing from the negative plate to the positive plate undisturbed. How the hole is moving? So suppose the hole is here. Now due to the potential barrier applied here, what happens? An electron experiences a pull towards this hole from this side. So this electron can get dislodged and combine with this hole, and this place will become a hole now, and then this particular electron can get freed and come to this hole, and hence this will become a hole now. So in this way, a hole, it looks as if the hole is moving from this position towards this position through the path A, B, C, D, E, F. Okay, so you read this paragraph, you see that when a valence electron at point A moves to the left, it creates a new hole at the point A. Effect is the same as moving the original hole to the right. So in this way, what happens? The valence electrons are actually the valence electrons are moving in the path shown by the arrows here. However, it when you see from the perspective of a hole, it means that the hole is moving in the opposite way, which is along the path A, B, C, D, E, F, and acting similar to a positive charge. However, one thing to remember is that this free electron flows from this position to this position and gets into the conductor. So suppose there is a wire here, suppose there is an outside wire, then this free electron can go inside the conductor. However, this hole, the hole cannot leave the crystal, the hole cannot leave the silicon crystal. An electron from this negatively charged plate can come and combine with the hole. Okay, but the hole is not leaving the crystal. This is an important difference. So you read all this 2.5 also you will read, and you will understand that what is happening. So there are two types of current in an intrinsic semiconductor. One current is due to the movement of the free electrons, another current is due to the movement of the holes. Okay, they move in opposite directions, and we can, from now on, we can visualize the current in a semiconductor as combined effect of two types of flow: the flow of free electrons in one direction and flow of holes in the other direction. These two, the free electrons and the holes, are called carriers because they carry a charge from one place to another. They are called the carriers, intrinsic carriers. So if you are talking about, someone is talking about the intrinsic carriers means the free electrons and holes in an intrinsic semiconductor. When a semiconductor is in a pure crystal state, every atom is the same atom, same silicon atom. then there would be some free electrons and holes. They are the intrinsic carriers. Okay. So now this is not much of use. When we have a intrinsic semiconductor, it is not we cannot use it. It is like an insulator, so we cannot use it for some work with current and voltages. Okay, so it behaves as if it is a insulator. What we need to do is we need to increase the amount of carriers. We need to increase the number of free electrons and holes in the semiconductor. How we do that? We do that by a technique called doping of a semiconductor. The doping of a semiconductor can do two things. One style of doping will increase the number of free electrons. Another style of doping will increase the number of holes. So let us first try to understand how we can increase the number of free electrons. What they do is add a pentavalent impurity. Pentavalent impurity means we add some pentavalent atom. Pentavalent atom means an atom which has 5 electrons in its valence shell. A pentavalent atom is added to the silicon crystal. Obviously we cannot add it in solid form. We have to first melt the pure silicon crystal, and in that molten state some impurities are added, some pentavalent impurities are added, and it becomes a homogeneous mixture, and then it is solidified into a crystal. So it becomes a impure silicon crystal with pentavalent impurity. When we have a pentavalent impurity, then what happens? You see this picture. Suppose we are talking about what are the some pentavalent impurities. Some things are written here, arsenic or something, I don't remember much here. Yeah, arsenic, antimony, phosphorus, these are some pentavalent atoms. So suppose we have an arsenic atom at the center. Please remember this in mind, that impurity means the number of pentavalent atoms are much less than the number of silicon atoms. That's why it is an impurity in the silicon crystal. Okay, the number of arsenic atoms are much less than the silicon atoms. Suppose this central atom is an arsenic atom. It has 5 electrons in its valence shell, and these are silicon atoms. So when the silicon atoms will combine with the arsenic atom, each of the silicon atom will donate 1 electron. So total number of electrons in the valence shell will become 5 plus 4, which is 9. But we know that the stable valence shell has capacity to hold 8 electrons only. So what will happen? The 9th electron or the extra electron will come out of this shell and go into a higher orbit and become a free electron. So in this way, the number of pentavalent atoms that we add in the pure silicon crystal, those number of free electrons we will readily get. Those number of free electrons. So here now we have a control on the number of carriers that we wish to produce within the semiconductor crystal. Do you get me? So with the help of the impurity, we are having a handle on the number of carriers that we wish to produce within a semiconductor crystal. The more the impurity, the more the number of free electrons. The number of free electrons is exactly equal to the number of pentavalent atoms, number of impurity atoms present in the crystal. There would obviously be additional free electrons and holes due to the thermal energy that we already have talked about, we already have known. So that those are the intrinsic carriers. Those are the intrinsic carriers. However, additional free electrons we are creating by imposing the impurity. Okay. So these are each, you see this in this paragraph, each pentavalent or donor atom, they are also called donor atom because they are donating an electron, an additional electron. They are called donor atoms because they are donating additional electrons. So this is how a manufacturer controls the conductivity of a doped semiconductor. Obviously, more the impurity added, more becomes the conductivity. How to increase the number of holes? So we have studied how to increase the number of free electrons. Okay, one point I want to mention. Please remember that there is the net charge of the semiconductor crystal is still 0 because the number of electrons and number of protons are the same. Though we have been able to increase the number of free electrons inside the crystal, but the number of electrons and number of protons are same because we have not taken away any positive charge or we have not thrust in any additional negative charge from outside. So please bear this in mind. So now how to increase the number of holes? To increase the number of holes, the impurity that we add is a trivalent impurity. Trivalent impurity example are aluminum, boron, gallium. These are trivalent atoms. So what happens? Look at this picture. So the central one is a trivalent atom. It has 3 electrons in its outermost shell, receives additional 4 electrons from neighborhood silicon atoms. So its valence shell now has 7 electrons and there is a vacancy. So this vacancy that we are creating in the valence shell of the trivalent atom will behave exactly as the hole that we have already studied. It will behave as a hole. It will accept an electron from an adjacent atom, fill itself in, and from where the electron has come out, there will be a hole created there. So in this way, we are actually creating holes in the valence shell of the trivalent atoms, which we are coding in as an impurity in the silicon crystal. So please remember that the holes are getting created at the valence shell of the trivalent atoms. Okay. Obviously, intrinsic holes and free electrons were already there. These are additional holes getting created due to the addition of the impurity. These are also called, that this trivalent atom is also called an acceptor atom because it will accept a free electron during recombination. This hole will accept a free electron from the lattice and recombine. So it is an acceptor atom. And so what are the points to remember? That we must produce the semiconductor as a pure crystal before doping, and we can control the amount of impurity, and by controlling that amount we can precisely control the number of free electrons or holes in the semiconductor. So we are actually controlling the conductivity property of the semiconductor. Okay, some historical points. Historically, pure germanium crystals were easier to produce. This is why earliest semiconductor devices were made of germanium, but eventually silicon crystals were easy, manufactured techniques improved and pure silicon crystals became available because of its advantage, and also silicon is abundant in nature. In our earth, it is the second most abundant element present, silicon. The silicon is available in the sandy beaches and all. Within sand, sand is basically silicon oxide, some form of silicon oxide. So because of that advantage, silicon become the most popular and useful semiconductor material. So this is so this is about the doping, and these two types of doping gives rise to two types of extrinsic semiconductor. We talked about intrinsic semiconductor, which is the pure semiconductor. Now we are having impure semiconductor, which are called extrinsic semiconductor, and the semiconductor which is having pentavalent impurity giving rise to excess of free electrons are called N-type semiconductor. Okay, because the majority carrier now, I hope you understand why this is called majority carrier. Majority carriers are now the free electrons, because free electrons are now much more than the number of holes. Holes are created only due to the ambient temperature. Free electrons are created due to the ambient temperature as well as the impurity. So they are the majority carriers now. So they are called N-type semiconductor. N stands for negative, because the majority carriers are electrons, that's why negative. However, the crystal is not negatively charged. Please bear this in mind. The crystal is neutral. Number of majority carriers are free electrons. Since electrons are negatively charged, it is called N-type semiconductor. The other type is P-type semiconductor. When it is a trivalent impurity, when we have majority carriers as the holes being positively charged, so holes having the notion of positive charge, it is called P-type semiconductor. What will happen? So let us learn till this. We are not going to the unbiased diode. We would stop here with N-type and P-type semiconductor. But there is one last point to be added here. When we have an extrinsic semiconductor, it is either N-type or P-type. N-type means majority free electrons, P-type means majority holes. So when we have an N-type semiconductor and we apply a battery across it, look into the picture. This, we apply a battery. What will happen? Majority carriers are the free electrons. They will experience a pull towards the positively charged plate of the battery, and they will move from, in this particular picture, the electrons are moving from right to left. So a current, also the holes are there, the holes as if they will move from left to right. However, the net current, you can easily understand, we are becoming sure now that the net current there will be a net current which will be from left to right, because the electrons are moving from right to left. So the net current will be from left to right. Similarly, for P-type semiconductor, what will happen? These are holes, they are not moving outside, but what is happening? Charges from the battery are coming here, getting recombined with these holes, and then again moving outside the crystal from this end. So there is a net movement of electrons in this direction from right to left of the crystal, and applied voltage, the free electrons move, these are the free electrons, they are moving from moving to the left, and the holes are moving to the right. Holes are moving to the right means actually free electrons are coming from outside, getting recombined with the holes. It looks like the holes are moving from left to right. So what is happening? A net current is getting experienced from left to right in the p-type semiconductor. Okay, so this is about the n-type semiconductor and p-type semiconductor. In both cases the direction of current remains the same. Okay, so it behaves as a conductor basically. So in the intrinsic semiconductor it behaved as an insulator. What we have done, we have doped the semiconductor, we have increased the number of free electrons or holes. So number of free electrons getting increased gives rise to n-type extrinsic semiconductor. Number of holes getting increased gives rise to p-type extrinsic semiconductor. We don't need to mention the term extrinsic anymore, n-type and p-type. And when it becomes an n-type and p-type semiconductor, it basically increases the conductivity property, so it moves from being an insulator to a conductor. Some level of conductivity is there, and we can have a control on the level of conductivity by increasing the impurity. But still you would notice that we have not encountered any nonlinear phenomenon. As much voltage we are giving, that much current we will get from the device. Okay, so there is no nonlinear phenomenon till now. The behavior is same as a conductor and an insulator, which are linear elements. How the nonlinearity comes into picture, that we will discuss in the next class, when we will start studying the diode, which is the first device of concern. So remember that intrinsic semiconductors as well as extrinsic semiconductors are not the elements that we are using in the circuit. The elements that we are using in the circuit start from the diode. But to study the diode, we need to understand what are intrinsic semiconductors, what are extrinsic semiconductors, how we are dealing with, how we are giving, what is pure crystal, what is impure crystal, how the impurity makes a difference, what are free electrons, what are holes, or what are carriers. All these concepts need to be very clear in our mind. So you study this chapter, the second chapter from Malvino, and there is a corresponding chapter in Boylsted also. Study the entire chapter of semiconductor, also study the diode. You will be able to study the diode also on yourself. Next day I will go through the diode. So with this
Sir, you are muted.
Okay, now?
Yes, sir.
So did any part of my lecture got muted?
Sir, you are again muted.
Now?
Again.
Someone is able to mute me. I don't know why, because I have started the meeting.
Sir, actually you are not the organizer only, sir, of this meeting.
Who else is an organizer? And how come another person can become an organizer?
You are organizer, but each and everyone is a presenter, sir, here.
Okay, so I have to...
So everyone can mute.
Okay, I will have to edit some control then. Now I will set up a recurring meeting. That is the best way. Last time also I did like that, but this time I am setting up instantaneous meetings. Okay, I will set up a recurring meeting. That time I will be able to control that. Okay, so I hope that no part of the lecture got missed. So I will leave the meeting now. and you study this chapter once from the book, and then we will meet in the next class. Okay, thank you.